I'm so excited to be here. Hey, Amitava. Hi.
Hi, Parul.
You can hear me clearly, right?
Yes, I can.
Yeah. So, welcome to our fourth episode of this entire webinar, Cut the Clutter series. How have you been doing so far?
I am doing great. I'm very excited about this seminar, except for one thing is I'm a little bit having flu symptom, but it's not a big deal. But I'm very excited.
Oh, so you're doing well now? Like, have you
Yes.
recovered?
Yeah,
Okay.
it's just a little bit of kind of, slight temperature, I guess, and some sore throat. So you will probably hear a little bit husky voice from me, but that's just because of the flu. But it's not a big deal. It's okay.
Yeah. So we have people joining in. So you know what, Amitava, as a ritual, it's always like since the past three webinars that we had, we have made it kind of mandatory for our speakers to share something really interesting or cool, which can fascinate our viewers and audience also. So, and it has nothing to do with, the webinar and what the topic is going to be about. So, do you mind sharing something interesting about yourself as well with our audience?
No, absolutely. I can do that. Yeah. I don't know if it is interesting, but I can certainly share something that I do outside of my work. So I have a 14-year-old daughter and she just started her high school. She kind of pretty much takes all of my free time outside of work. Whenever, however, I get a little bit of free time, I try to do some, involved in some water sports, which is like I do boating, a motorboat, kayaking, jet skiing, stand-up paddle boarding. So I love, that kind of sports. Also, sometimes, depending on the weather, I do a little bit of uh, rollerblading as well. So I'm involved, in some activities that are fun for me. Yep.
Like what? Like what are those activities which are fun for you?
So all of this, like particularly boating, so the on the Northeast River here, right outside of like a Baltimore area, I go for boating there, and it's very nice, beautiful there. Wherever you go out, on vacation or let's say weekend getaway, try to do, jet skiing, that kind of thing. Also kayaking, stand-up paddleboarding. The Chesapeake Bay is right here where we live close to, that. So all of these activities, these are really very fun activities for me. And I've been doing that actually for some time now, over
And
the
you always
years.
take your daughter along with you? Like,
Yes, yeah. So she's actually a better swimmer than I am. So she's part of the swim team. So she's very brave.
that is
And
nice.
yeah, yeah. So she has a lot of courage of doing that. And sometimes she actually goes on swimming on the river itself. So yeah, and then tubing, she does tubing. So this is all fun activities, I guess. Yeah.
Yeah, that's pretty cool. I mean, I didn't know about it. I think the audience might be enjoying, with whatever you have to share. Thanks for sharing.
Sure.
So I'm guessing a lot of people have started joining in. Uh, let's give them a couple of more minutes, before we start off.
Sure.
So, meanwhile, let me start by welcoming all of you. Good morning, good afternoon, folks joining in from the US. Good evening to the folks joining from Europe and Asia. So, while we have people still joining in, let me just take this moment to share a few housekeeping rules. This webinar, as you all know, is going to be a 1 hour session, and we have our speaker Amitava, who's going to present it for the first 35 to 40 minutes. The second part of the session, or the last 10 to 15 minutes, will be dedicated to answering any questions, thoughts, feedback, or doubts that you have. And then the last 5 minutes will be kept for the closing comments. On the bottom right side of the window, you will find a Q&A box where you can drop your questions. And towards the end of the sessions, our speaker will take those questions up. Okay. And of course, once the webinar is over, and if you've already registered, you will also share the recording of the session. Um, so these are certain, housekeeping that you can follow. And now I thank you for all the time that you've taken and joined this call. And we look forward to a very, very enriching session with our speaker today, Amitava Gangopadhyay. So before we kind of have him take over, there is a bit of introduction that I'd like to give about Amitava. So Amitava is an experienced data science professional. He has experience in both academic research and building ML AI solutions in the IT industry. He did his PhD from the University of Maryland and worked on a postdoctoral research project for NASA. Amitava has multiple publications in peer reviewed, highly rated international journals and conference proceedings. He has taught and mentored many students from multiple universities in the United States and has also served as adjunct professor, senior thesis advisor for computer science students, and is been invited at several US universities so far. As for the IT industry, Amitava has extensive experience in developing end-to-end solutions involving machine learning, deep learning, and artificial intelligence. He's currently working as a director of analytics at FactSpan and serving multiple of clients. So, okay, I think I have not missed out anything as part of your introduction. But now the floor is all yours, Amitava. Please, go ahead. You can proceed.
Thank you, Parul, for all those kind words. I hope I can measure up to those words in today's session. So hi, everybody. Good morning, good afternoon, good evening, depending on where you are. Thanks for joining this webinar session. I'm really very excited, to talk about some of the work that I have done. And I have always been very kind of passionate about some of these results, from these projects that I did recently. So let's get, dive right into it. The topic, I kind of phrased it like some atypical data science approaches to solve common business problems. And the reason I call it atypical, I'll get into more detail about that, in the next slide. In the meantime, let me mention that all the use cases, the work that I will talk about today, these are all published work, and I will very quickly show you. These are all published papers. So, for example, this is one for for one of the use cases that I'll talk about today. And then there is another paper here. This is for fraud detection, and this is for entity resolution. So if you are interested, in taking a look at these papers, please let our marketing team know, and I will have their, contact address at the last slide. For anything related to this webinar, please contact them. I can also be contacted directly if you have any question about the material that I presented today. So, as I mentioned in here, today I would like to talk about 3 use cases. However, in the interest of time, if that doesn't become possible, I will realize that, as we approach, I at least want to focus on the first couple of use cases, maybe go into a little bit more detail, and then depending on the time that we have, we'll talk about the 3rd use cases. Okay. So again, the reason I wanted to call this as atypical methods is, for example, in the financial fraud detection use case that we worked on, and again, this was a collaborative work, with some computer science students, some university professor, some director of Elsevier lab, and these are all published and presented at Big Data Conference. During the time we are doing working on these use cases, kind of realized that in the industry, typically for machine learning AI solution, usually the the enterprises, the organizations, they build one solution, and that's pretty much like all encompassing and one single, usually typically one single model. However, what happens is, because some of these problems, they are very common, but at the same time, so complex that, and the data, the nature of the data changes with time, sometimes it becomes hard to build a model that will stand the test of time. One particular model algorithm can have bias to a certain kind of data. It may work well for certain kind of data. As the data changes, then it may not work. Its performance may degrade over time. Also, some of the use cases, these are very mission critical, and we can afford to make wrong predictions, that frequently. So how do we, build a solution that is robust? So for that, some of the things that we did was, number one, we wanted to avoid the over reliance on a single ML model, or solution. And then also we took phased approach. So rather than just like one single machine learning model and that makes the prediction, we will go through phases of analysis and modeling, and then we'll make the final determination or final, predictions or forecasting, as the case may be. Thirdly, the innovative approach we used in one particular use case, and that's for data leak prevention, is we use the metadata from the training records rather than the actual field values. And that was kind of an innovative new kind of solution. And that was one of the reasons we were able to publish this, is because this was something new at the time. And then one other thing we use this technique is a positive feedback loop. So some of the predictions, forecasting that, when we get the results and we realize that, that results that was miscategorized or misclassified, then whenever it goes through manual review, or let's say some flexible rule-based, automated review, and then, make the correction, we can add that corrected data back to the training data set. We can, append it. That way, next time, when the model sees similar data, it will make the correct predictions. So it has a positive feedback loop built in, and that will improve the performance of the model. So in case of financial fraud detection, what we did was, and I'll talk about that in a little more detail. First, there was a dynamic statistical analysis part. Then there was machine learning. Then there was deep learning. And it goes phase 1, phase 2, phase 3. If it fails on the phase 1, and it needs to be, it flags the transaction as a suspicious, then it doesn't need to go through machine learning and deep learning, because those are computationally more expensive processes, and not every single transaction needs to go through machine learning and deep learning. If it is an obviously suspicious transaction, we can flag it right there. Similarly, for data leak prevention, we used metadata, like I said, as opposed to the actual field values, and also used multiple models, okay? Not just one single algorithm, but multiple models. And then we use the majority voting classifier, so to avoid that over-reliance on a single model. And then for the entity resolution, we used high-performance lookup using multiple different approaches. And then also in the phase 2, we use machine learning models. So here is the the background on the organization where we conducted this kind of research work, and then finally 2 out of these 3 use cases it actually went to production. So it's not just pure fun academic research, but they are useful, and we actually deployed them to production. So when I started this work, I was hired as the principal data scientist globally, and this is a large global financial services organization. And in fact, this is the largest financial services organization that provide secure messaging platform for all the banks globally, more than 10,000 major banks, including all the US banks, major banks like Bank of America, Wells Fargo, Capital One, all of them. So they use their network. What I can share here today and how much we can talk about, in terms of very specific information, there are some restrictions. So I will talk about only as much as I can, and I'm allowed to. So their core business is provide secure messaging platform, and particularly for cross-border money transfer. So the data security is their really core business, okay? And fraud detection and notification was not part of their business really at the time, but then they realize that there is a lot of opportunity there because they're getting all these transactions coming from, all over the world from all these major banks. So if there is a way we can identify one single fraudulent, entity, then we can flag that entity and then send notification across the network to all the major banks, and then potentially stop a lot of money laundering efforts, globally. So there was opportunity there. So when I joined, they did not have, any structured or even in fact, no data science effort really. They wanted to find out how we can use data science, machine learning, AI, to improve their, their business or add value. So I started working on those three use cases that I talked about in the previous slide, and I built small prototype solution with some synthetic data and some anonymized data also. Then presented it to the executive board for executive buy-in, and then finally they were very excited. They saw the opportunity there. Then finally I got a green light to go ahead and then build the solutions and build an on-prem infrastructure. So I'll talk about that on-prem infrastructure also. So then, I went ahead and hired, 5 University of Virginia computer science students, and then worked with their professor, and then started working with our DE DevOps team and then legal team for, so that we are all aligned on the data use, and then business stakeholders. And then 2 out of 3 use cases, we actually, went ahead and built production grade solution. And then, as I mentioned, this has been published all 3, papers in conference. With that, as for the on-prem infrastructure, so at that time, what I realized was that we needed to have, build some deep learning solutions. So I ordered, NVIDIA GPU-based workstations for to build the development environment. And that's where, we're doing all this experimentation. Then with the help of the infrastructure team, we built out a 6-node Hadoop Spark cluster and then added our NVIDIA, GPU-based deep learning server as an edge node to that. And that's where we are kind of, deploying these, solutions. In terms of the technology stack, using Scala and Python. So one particular solution, we built the data pipeline and even the machine learning model and everything with Scala. And the 2 other were, using Python. Go, we experimented, then we realized that, at that time, the library was not really as enriched as, for example, say Python. So we kind of focused on primarily Scala and Python. Then, this was for the data pre-processing, Spark. So our data was primarily Hadoop and edge-based. And for machine learning part, so using, of course, Anaconda, scikit-learn. And then for Spark, using Scala, we are using ML and MLlib. And for deep learning part, using primarily TensorFlow. Then for the deployment framework, it was with Scala, it was the Legom framework that we're using. And for with Python, deploy the solutions as REST API using an Apache Flask. And then on top of that, they had already, for the client already had some simpler analytical, data pre-processing dashboarding tool, using the Elastic Stack. So Elasticsearch, Logstash and Kibana to show some of the primary, preliminary results. So that was the, on-prem platform. Now let's get into the fraud detection, the financial fraud detection, use case. So this is a big deal, really. Fraud detection, it's a multi-billion-dollar problem, and we need a robust solution. It cannot be, we cannot have one single magic bullet solution that solve all type of frauds, because fraud comes in various forms, from various sources. And we cannot just have one single solution. So we needed to focus. And as you can see here, this is the, PwC's Global Economic Crime and Fraud Survey this year. And so in various different industries and domains, like industrial manufacturing, financial services, and all that. So the proportion of, fraud transactions is actually varies, based on their source and the type of industry. And it also varies on the left panel, you see, the percentage depending on the size of the organization. Our organization, for that financial services, we wanted to focus on the customer fraud because cyber crime, is a different beast, and they have different solution for that, whole different ball game. And then you have the know your customer, KYC, is also a whole concerted effort that they follow to find out that they are actually onboarding the right legitimate entities, into the platform. So those are separate efforts. Here, what we wanted to focus on was identify the transactions, okay, that are coming through as secure message, encrypted messages within the platform. And then if we can identify anything suspicious about those transactions, and if we can flag them. So that was the purpose. One of the reasons this was important is because this money launderer, what they do is when they are trying to launder money and let's say send money from one country to another, cross-border payments, they try to restructure the transaction. So if it is a multi-million-dollar transaction, they will break it down into smaller transaction dollar amount and then send multiple ones. Okay, so that just to evade the federal regulation on reporting. So that anti-money laundering effort, and then prevent the objective was to prevent financing for terrorism or illegal activities. So how did we build this solution? First of all, here again, just to emphasize, stress that point that security comes in different layers. There is no one silver bullet solution, okay, that we can build. So bot mitigation, device ID telemetry, behavioral biometrics, all of these different phases, different layers, and fraud or suspicious activities get identified accordingly, Then we have this transaction and event monitoring. And for that, within that, we are focusing only on pretty much this part, payment or fund transfer. So that's the part we are focusing on. The approach that we wanted to take was the transaction and event monitoring. First, there will be some rule-based, okay? Some clear-cut, well-defined rules that we know that define what is fraud versus what is not fraud. If we can identify through those hard rules, if a transaction is fraud or not, it gets stopped right there. Then it goes to the next phase, which is the dynamic statistical analysis, and I'll talk about that. Then it goes through the MLDL-based solution, the machine learning, deep learning. If, let's say, for example, it passes through these stages, then it gets approved. If at any point it is flagged, it can be flagged for review, or it can be stopped if it is that clear cut. And for the review part also, there could be automated review. It's based on some flexible rules. And we can devise these rules in terms of the customers, their risk tolerance or risk appetite. If they say that, okay, if it is a low dollar volume, low dollar transaction, less than $100, we don't have human resources to review each and every single transaction like that. We are okay, we can pass them. So we can make flexible rules like that. And otherwise, if it needs manual review, then it will go through manual review. So the points to note here is fraud detection, number one, as I said, it takes place in layers. Okay, it's not one single layer, not one single tool, not one model. Number two is what goes for review is really a function of risk tolerance. If they have high risk appetite, then we build flexible ones. If it is the low risk appetite, then it will be very tight, very restricted, very conservative review criteria. So for the dynamic statistical analysis part, what we did was, look at 5, different banks. There are 18 months of records, transaction records, and globally, in different parts of the world, to make sure that there is no geographic control on the data that we are using for training models. And each individual bank, we built individual model for them. We cannot just group them together and expect that one single model, one size fits all solution. It's just simply because their transaction pattern, what is their working day versus what is their non-working day, half working day, those things are different across different parts of the globe. So based on, type of the day, like full working day, part working day, non-working day, holiday, we built a transaction-based calendar. Okay. What time do we get the first transaction that comes into the platform from that particular bank? When do we get the last transaction? So that's the window, business window. Then within the transaction count, for transaction counts, within, let's say, 15-minute rolling window, we want to find out what is the arithmetic mean, what is the moving average, and sometimes, the exponentially weighted moving average, because that always takes consideration and gives higher importance to the latest values rather than values, out in the past. So, and then, of course, standard deviation. Standard deviation, we can take 1 sigma or 2 sigma, depending on their risk tolerance. And then we can build a transaction profile day by day, hour by hour, within 15-minute window for that bank. And then when, let's say, for example, today, at this moment, we get, a transaction, 120 transactions coming in to our platform from Bank of Bangladesh. And we figure that's suspicious because we never get, historically those many transactions for that high dollar amount. So those transactions, depending on which one falls outside of this error envelope, they will be flagged. Moving on to the next one is the second phase. So that was the first phase in the last slide that I showed, statistical analysis. The second part is the machine learning part. And for that, it's a, SARIMA model, it's seasonal ARIMA model, auto regression, regressive model, but it takes into consideration the seasonality within the data. So basically, although it shows that the equation, it's a complicated looking equation formula, but it's not really that complicated. All it's doing is basically the non-seasonal and seasonal, the auto-regression part, it's multiplying that with non-seasonal difference and seasonal difference, and equating that with the non-seasonal and seasonal moving averages. So that's the governing rule for this model. Now, the way it works is we look at the historical data, for example, the top left panel, and you see that's the actual, transaction. And this is for illustration purpose. This is not the actual data from, from my client, because there was some restriction, I cannot show that. So here, this is, let's say the actual, data. We decompose that transactions, a time series data into trend and seasonal. Okay, once we decompose them, then we end up having the residual part. Once we take out the trend and seasonal part, then we can see from how the distribution of those residuals plot along that zero line. If it is kind of uniformly distributed, across the line, or plot right on the line, so that means the decomposition and the model actually work well. On the right-hand side, and showing that the actual versus predicted. So once we build this model, then when the new transactions come in, they pass through the model and it will make forecasting, time series forecasting, and then it will show that, what is forecasted versus actual. Now, if we look at some historical data from prior, and we can compare them, along with the forecasted values, then we can see how good the forecasting was. So this is how the SARIMA model was built. And now this is actually the real data that we got out of our model. And here you can see, 2118 to 228. So that's like, a 10-day window. And so day by day, and it shows the actual versus predicted. And we are showing here this large error, but it's basically because we are taking like, kind of a conservative error estimate, which is the 2 standard deviation. But it kind of follows the pattern, and it shows closely approximates the values between the actual and the predicted. So that was the result from the SARIMA model. Then the next phase is about the deep learning phase, where we use 2 different models. One is autoencoder, and another is restricted Boltzmann machine, RBM. They work kind of, in the similar way. So the idea here is, in this particular implementation, this is not really a deep learning model per se, because this is a more of a shallow learning. We have only one hidden layer, but that works really well, for our solution. So here, for example, we are looking at all these different features. So like message type, is it a retail money transfer versus bank-to-bank transfer? That kind of message type. Okay, what day of the week? What is the dollar amount? The message count, how many transactions are we getting within the time window, all of that. So that's the input layer, 24 nodes. And then it goes to the hidden layer, which is 4 nodes. what it does is between the input layer to the hidden layer, it encrypts all that input features, right? Input features, and then going from the hidden layer to the output layer. So output layer is, of course, again, it's 24 nodes. It decrypts that. Whatever it encrypted, now it decrypts that, and it tries to compare between what was input versus what is output and what is the difference now. Can it, bring the original value back? How far off the, unencrypted value is from the original value? That gives a measure of what is called reconstruction error. Now, we have used both good legitimate transactions and millions of those. And then we also use a lot of synthetic, artificial, synthetic fraudulent transactions that we created based on our business knowledge, that what can be potentially, fraudulent transactions. We pass them through this during training and then find out what is the threshold that we need to take cut off to determine which one, is a fraudulent transaction versus what is a legitimate transaction. And that's through that experimentation, trial and error, okay? So through that process that we find out that, okay, this is the threshold that we want to use for fraudulent versus, legitimate transaction. Now, when a new transaction comes in, it does the same thing. It extracts all those features. It goes through this, neural network. And then finally, it makes a prediction that if it is beyond, the threshold, it will be flagged as a fraudulent transaction. One performance measure, which is very critical for this kind of solution, is what is called sensitivity. So typically people talk about confusion matrix, true positive, true negative, all of that, false positive, false negative, and accuracy, precision. In this type of use cases, what really matters is, this is the needle in the haystack problem. We have millions of legitimate transactions, and there will be just one single fraud transaction. If the model fails to identify that fraud transaction, our accuracy value would still be very high, but it defeats the purpose. It defeats the purpose of the model, because that's what we are looking to do. We are just looking to identify that 1 in a million fraudulent transaction. So sensitivity is the critical measure there. Now, just so you know, for this solution, what we did was we also had some real, fraudulent data that were kind of, identified and flagged through other means before, and we used them, passed them through our solution, and there are 27 of those. And then 26 out of those 27, they were correctly identified through our phased approach of this solution. And that was pretty, impressive at that time. So that's the first use case on financial fraud transaction. And I think we are doing okay time-wise. Now it's 1:33. So I will move on to the next use case, which is called data leak prevention. And again, for this particular client, their core business is provide a secure messaging platform. So naturally, the protecting the data, the privacy and the security of the data, is the critical part of their business. So what we wanted to do was, they have in the production environment this data lake, and in the data lake, all these logs, raw log data are coming in from variety of system, management system sources and different apps. They're writing those logs into the data lake, and that's in the production environment. And those are exfiltrated logs they get through filtering, different rule-based, hard rule-based criteria. They, get filtered, and then they come to the non-production environment where we run different analytics on. So the point here was, the use case was to make sure that when we are moving data from the production environment to non-production environment, we are not, no sensitive information is being leaked. Number one. Number two is try to prevent a hacking event. Let's say when a hacker wants to get the data from the production environment log data, and that log data can have some PII data also, and also bank information, a dollar amount, all of that. And they want to, let's say, encrypt some of that data and smuggles that data out of the production environment to the non-production environment. Okay, how can we prevent that? That was the use case. So here, basically what we did was the first the ML model training and testing phase. So this actually was the initial numbers, but we went ahead with much more data. So for example, here I'm showing 4 million logs and 1 million. It's actually a lot more than that. In the final training, it was like 17 million data log records. So what we are doing is we had a custom program that we wrote that extracts the metadata out of those log records. So in the log record, and I will show that in one of the slide, next slide here. So in fact, let's talk about it right now. So here you see there are different fields. So the UUID, app name, the log type, flow type, these are different fields within the log. And what it is doing is this custom program is extracting the metadata out of that, trying to find out that is that field, is that alphabetic, numeric, alphanumeric, okay? It's not using the actual value of that particular field, but rather it's extracting the metadata. And is alphabetic field becomes 0 or 1. So if it is alphabetic, then is alphabetic is 1, otherwise it's 0, like that. So it's 0 or 1. This is how we are building the feature matrix in this case. And this was, excuse me, at the time, a little bit of a new approach where people typically use the actual field value rather than the metadata. So we use that and then build this. So then you split the data, of course, into 80-20, get the training data and the test data. And then, build supervised morning ML model training and testing that we do. And in this case, we actually use three separate models. And these are all tree-based. One was decision tree, random forest, and XGBoost. So boosting and bagging technique were also used in those two models. Once we train the model, that trained model is actually being used for the live streaming data. Same thing happens. The same custom program extracts the metadata out of those logs, and then feeds that data, that extracted metadata, that feature matrix into the model, and then it makes prediction if it is good versus suspicious. Okay. So this was how the model was built. One critical feature engineering that we did and that works really well is what is called Shannon entropy. And Shannon entropy is essentially it's a measure of how much of information is contained within a field or the uncertainty that is inherent to its possible outcome. And this is expressed in terms of this H, which is the Shannon entropy. It's basically the probability of that value, what's times. You take the log probability of that and you sum that for that whole variable, and take a negative of that. That gives you the Shannon entropy value. The way we and then for the way we used it is for each field from the log, we encrypted those fields, okay, some of the specific fields, and then we took the Shannon entropy value of the encrypted field versus the original metadata value, which is the unencrypted value. And then we could see that there is a vast difference between the encrypted versus unencrypted values. And that gives us the resolving power to identify what is a fraudulent transaction versus what is a legitimate, actual, good log record without sensitive information versus what is a suspicious, log record. The reason being, like I said, there is a possibility that a hacker, and we all know these hackers, they are pretty smart people. They know, what they are doing. They can encrypt some of those critical fields if they get access to that and then smuggle that out of the production environment. And what we did was in our case, so we just needed to stay a few steps ahead of those guys, those bad guys. One of the encryption technique that's used and it's considered as the best in the industry is AES 256-bit encryption. So that was one, and then there are other techniques also. And for the text data, so text to hex, hexadecimal encryption that we used, and then we could get those two values, entropy values for encrypted versus unencrypted, and use that as the engineered feature for our feature matrix for the model. And here you can see that some results. So DT is decision tree, random forest, and gradient boosting tree. So here the accuracy is very close to 1. Excellent results, that we got. And this was very important because if the model, let's say, misclassified as a record, as a log record, as suspicious, and it blocks its passage from production to non-production environment, that will have a negative impact on the downstream applications. So we need to be careful about flagging, what we can flag or what goes for review, and how confident we are about that detection process. So that's why we used multiple models, and then we did a majority voting. And here you can see, for example, the RF model, random forest, it gives like 99.9, whereas when we do the voting, then we get like 100% accuracy there. In one of the particular metrics that people use to find out what feature actually contributed most for the predictive power of the model, and it's a feature importance. And here, and I cannot really mention what feature is what. So you can see there are like more than actually close to 100 different features that we use, and one particular feature was actually very significantly it contributed to this high predictive power for the model. Now, I want to check real quick, yes, so we still have 4 more minutes. I can talk about very quickly, and then we can take questions at the end. The last use case that we successfully also built a solution for is what is called customer address entity resolution. And here, basically, for this particular use case, so customers, retail customers, they go to bank and they, let's say, someone wants to transfer some money, small amount of money from here, United States to Mexico. And they, type in or give like a wrong, inaccurate address, which is pretty close, but still inaccurate. Or even sometimes in extreme cases, the address just doesn't simply exist. So what happens is when these transactions are taken into the platform, it goes, through this, and it just, increases the network traffic, and it comes back as undelivered because the recipient was not found. So how do we solve this problem? So this is a textbook example of entity resolution, how we can find out what is the closest match between what the customer typed versus what should be the correct actual address. So what we did was, this is because this particular client has all these historical records. So we could, use those millions of different addresses, globally from, excuse me. And then we could use that as like a clean gold copy of records and use that for, to solve this problem, not necessarily in 100% of cases, but there will be a high percentage of cases when we could, the model can predict what the customer was trying to, type in. And it will make suggestions at the interface level. Did you mean this? And that will happen because we have the clean records. And then if it fails, let's say the model cannot, predict anything close to that, then there is this Google API address services. That's a paid service that the client can use for those, selected, cases. That way, we don't have to pass through all these, incorrect addresses through the network and then get them back. So the way we did that was, again, phased approach. First, the input data, it goes through some preliminary lookup. And one is called PySolar. PySolar is essentially a Python wrapper around the Solar search engine. Okay? Soda is a package that, my collaborator, Sujit Pal, is the director of Elsevier Publishers. So they used it extensively. He built it. And they used it for to find out patent fraud. If somebody has already published a paper similar to what this new person is claiming as a new work, so it will go search and find out similarity. So that package works really well, and we use that solution here. And he is, of course, one of our collaborators for this paper. And then here, another one is called record linkage. So what it does is all this high performance lookup, it goes through and it finds out if it can find, an exact match, or what is the, it will rank the, the level of match. What is the confidence level? What is the closest, match with what we already have? Then it will kind of, ask the customer to confirm. If let's say it cannot find that match, then it goes through a more computationally extensive phase, which is the ML model. And for that, we use dedupe. And dedupe does a pretty good job, in resolving some of those ambiguity in the addresses. And I will show some results in the next slide. Then let's say if it fails, ML model also cannot find, then there are two options. One is, ask for more info, or like I said, the Google Service API, try that, paid service. And then if it's still, let's say, for example, there is no match, then of course, it needs to be stopped before it gets transmitted. So here, for example, some results, like which one worked better for what, in terms of performance. So these are like, in millisecond. So the performance of these different methods, it depends, is a function of what kind of match it is. So if it is an exact match, PySolar does, the best job. It's a very, and it's used in the industry, some big places, like I think LinkedIn, they use, and in other places, if it is exact match. Then if it is incorrect wording, also there, you can see PySolar, does, very good job for those preliminary lookup. However, if it doesn't find a match, then of course we have to use some other, like method, like, for example, dedupe. And in that case, dedupe works. It takes a little longer, but it can, find the match, the closest match. And here on this, Venn diagram, I'm showing what works better, like what kind of match works better for what method. So for the lookup method, we have this SODA, the package, PySolar, and record linkage. And I'm showing, like, if it is partly incorrect capitalization, so one word in the middle is, let's say capitalized or whatever. So that, like, record linkage can resolve those ambiguities and incorrectness, inaccuracies better than others. SODA does work really well for aliases. So for example, street spelled out versus ST dot. So that SODA does a very good job to figure that out, that it's basically the same thing. Similarly, dedupe model for, like, more complex type of match, fuzzy matching, and record by record, field by field comparisons, it does all of that, and dedupe does a pretty good job on that. So I think we are almost there, right? At the time, we are 47. So with that, I will stop here. And once again, I would like to thank you all for joining this session. I hope you enjoyed it. Once again, you can contact me directly about any specific, material that I presented here. However, for, webinar related, questions, and if you want to get like copies of the papers or anything else, please contact, here, this marketing@faxfan.com. With that, I will take questions if there is any question.
So folks, you can post your questions in the Q&A chat box, and we'll be happy to take those questions. I think, Amitabh, we've covered it really well, because I don't see any question in the chat box so far.
Okay.
Okay, we have one question. Is the fraud detection approach applicable for e-commerce?
Absolutely. That's a very good question. So the beauty of this kind of approach is it's kind of, flexible, and, it can, we can use this depending on the particular domain and depending on the, type of data. So the approach is basically, again, it's a phased approach. And, for e-commerce data also, you do the statistical analysis first, figure out what are the hard rules that you can build out of that, and what are the dynamic analysis that we need to do. Then you go for, like, the machine learning and deep learning part. So what I presented today, it's very analogous to really e-commerce data. So that the transactions, variety of transactions from different sources, different IP addresses, different banks, they're coming in into the platform. And then we are just trying to, sift through those transactions and figuring out what could be a suspicious versus a legitimate transaction. So it should work well. But again, it's just a matter of training it to the right level. Did I answer your question?
Yeah. Yeah. So they won't be able to.
Okay.
Yeah. Okay. So I don't think there are any other questions coming. In that case, we can end the session. We are 10 minutes early. Okay, we have one more question. 1 second.
Very good. So another question is soda. Yes. So this is not proprietary. The beauty of this, I like open source. I'm a big open source proponent, and my collaborator Sujit Pal, he developed this soda, and it's open source, and you can use it if you want. And yeah, just you can actually even do some search and then find out and you can use it. Yes, it is open source. Okay.
Yeah. So thank you, Amitava. I think the session was really, really enriching. Thank you, everyone.
Thanks, everybody. Again, thanks for joining. Bye.